hour hand broken off, how many hour possibilities are there for the hour hand within 12 o'clock and 2 o'clock? So we're looking, what are the possible, there you go. So 12 o'clock and 2 o'clock, what are our numbers that the hour hand could be at within that time frame? Just taking the actual number, just the full numbers. We have 3 possibilities. We have 12, we have 1, and 2. Those are our only 3 possibilities. Assuming we're just taking like the hour location. We're not worrying about like half an hour because that would give us we won't worry about that. In the total 12-hour period, what are how many possible locations are there for the hour hand? In 12-hour period, sorry. Just 12, yeah. And that could be anything from 1 to 12. Those are all the possibilities for that hour hand to be at on those clock periods. So if you want to find what is the probability of the hour hand being between 12 and 2, how would we find that probability? What did you say, Alex? Quotient. How would you do that? So the probability of being between 12 and 2 would be 3 out of the 12 options are the ones we want. And so if we were to divide that, 3 divided by 12, that would give us 0.25 or 25%. Either of those are correct. So we looked at the 3 possible outcomes that we wanted divided by the 12 total outcomes we have. And we'll talk about more specifically where we get this from. But before we jump to that, when I say the word probability, what do you think of? What does that mean to you? Probability. Ratios? Okay. What does it mean though? Yeah, it's our likelihood that an event will occur. So the likelihood that an event will occur. We use that word event a lot in mathematics when we talk about probability. So an event is anything that can occur. So rolling a dice and getting a 6, that is an event. Or getting a 1 is an event. Flipping a coin and getting a heads is an event. So we're looking at what is the probability of a certain event. How likely will that certain event occur? And the way we determine probability is kind of like what Alex said. It's a quotient. So probability the probability of an event, I'm just going to say event A. So the way we write probabilities, we like to put, whatever, I'll worry about that later. So the probability event, we typically put a big capital P, and then we put parentheses, and then we put whatever the event is on inside. So if I'm talking about the probability of rolling a 6, I might put P parentheses 6. That's reminding me I'm looking for the probability of getting a 6. So let's just say event A is some type of event we're looking for. So the probability of an event is always equal to the number of desired outcomes. So what are you looking for? How many possibilities are there for you to get what you want? Divided by the number of total outcomes. How many possible outcomes can happen? So this is really the generic basics of any probability. Number of possible outcomes or number of desired outcomes divided by number of total outcomes. So if we're rolling a dice and you want to get a 6, that one desired outcome is just getting a 6. That's your one outcome you're looking for. The number of total outcomes are all the possible numbers you can roll. Well, you can roll anything between a 1 and a 6, so there's 6 possibilities. So it would be 1 over 6 would be that probability. When we talk about probability, you can write it as a fraction, you can write it as a decimal, you can write it as a percentage. All of those are correct. Personally, I prefer decimals because they're the easiest to work with. Fractions, multiplying, adding fractions can be kind of annoying. Decimals are pretty easy. Percentages, it's just annoying having to convert from a decimal to a percentage and making sure your spacing in your periods are in the right location or your decimal points are in the right location. So personally, decimals, in my opinion, are the easiest to work with. And when you find a probability, you're always going to get a number between 0 and 1. So we'll always have a number between 0 and 1. And the reason being, 0 means something's impossible to happen. You can't have something less than impossible. It can't be below impossible. You can't have negative probability of something occurring. 0 is your lowest possibility. You can't have lower than 0%. 1 is the same as 100%. So it's impossible for something to be more than 100% likely to happen. It's either 100% that's your max, you can't go past that. You can't have something that's more than certain to occur. It's certain to occur. And so we will always get an answer on this spectrum. Well, we should never be outside. So if you ever get a probability that's outside of 0 and 1, then you probably did something wrong. We probably want to go back and check that out. We probably put our total outcomes on top and our desired outcomes on bottom or something like that. So we should always get something between these two numbers. And once again, the closer you are to 0, the less likely it is to happen. The closer you are towards 1, the more likely it is to happen. And then 50 or 0.5 is it's equally possible to happen, it's equally not possible to happen. That's your coin toss, your 50-50 chance. Does that make sense? Okay. So we have two types of probabilities that we'll talk about today. The first one being experimental probability. So experimental probability is you're creating an experiment, you're looking at something, you're creating an observation. And based off those observations, you're creating a probability. So you're looking at something and using that to sort of enhance or figure out what is the probability that's occurring. And the other one's a theoretical probability. So experimental probability and theoretical probability. Theoretical probability is actually thinking about something. You're not performing any observations, you're not doing anything, you're thinking about what are the odds. Like rolling a dice, I know how to roll a dice, I know what all my possibilities are, I know what I'm looking for, so I can use theoretical probability for that. I don't have to roll six dice 600 times to figure out what my probability is. And so the majority of the time we'll probably be looking towards experimental probability, but sometimes we will be using experimental. But let's look at this first. So a quality control inspector samples 500 computer monitors and finds defects in 3 of them. We want to find the experimental probability, so the probability based off this observation, that if I randomly selected a monitor, it will have a defect. So once again, probability, for the probability of a defect, probability is number of desired outcomes divided by the number of total outcomes. So if I'm looking for a defect, how many defects did I find? 3. So my desired outcomes is 3. How many total computers did we check though? 500. So 3 over 500 is my desired outcomes divided by my total outcomes. I can then divide 3 by 500, and this will give me my probability, which is 0.006. Once again, we're looking for between 0 and 100, or between 0 and 1. So 0.006 is between 0 and 1. It's very close to 0, so it's very, very unlikely to occur, but it has a chance.
But if it is 0, it means it's not going to happen.
It's not going to happen. And it is possible to get 0. Like flipping a coin and having it land on paw prints. Like some paw prints on a coin. You're going to get heads or tails. You can't choose the other one. And so the likelihood of it occurring on something else outside of those 2 possibilities is 0 chance. And so that would be a 0%. Or flipping a coin and it landing on one side of the coin, or a side of the coin. Yeah, so 50-50 for heads and tails. If I flip a coin and I just want it to land on the ground, well, it's going to land on the ground assuming someone doesn't catch it. Do something like that. So that's going to be a 100% chance. And so if all the possible outcomes are desired, then it's 100% chance. If there's no desired outcomes possible, then that's 0% chance. So we have a 0.006 probability to get our defective monitor. Now we want to think, that was just for one monitor. If I just pick one random monitor, I have a 0.006 chance of getting a defective monitor. I want to figure out, if this company manufactures 15,240 monitors, and I look at all of those monitors that month, how many of them should have a defect? So I'm going to take my probability, and I'm going to multiply it by 15,240. So the 0.006, that's just the probability for one event, just looking at that one monitor. So I'm looking at 15,240. So I'm doing that same thing 15,240 times. I want to see how many of those times should this odds come up. And if we multiply those two together, that will give us 91.44. So 91.44 times I should find a defect out of 15,240 monitors actually. But here's the question: is it possible to have 91.44 monitors? I'm actually going to round down because 0.44 is closer towards the 91 compared to 92, and so yeah, we'll have to round it, so we'll round that to the nearest whole number, which is 91. Computers or monitors, whatever. So out of those 15,240, I should find 91. It doesn't mean I will though. I could check 15,240 and get 3. I can check 15,240 and find all 15,240 of them are broken. It's possible, not likely. 91 should be the amount I should find. That should be the optimal number based off of our probability, but it doesn't mean it will occur. I could flip a coin 600 times and they could all land on heads. It's possible, but it's unlikely. It makes me think of, if you ever watched Dumb and Dumber, there's a scene where he goes up to ask the girl out on a date or something like that. I can't remember what it's going. And he goes up to the girl and he says, "So, what are the odds of you going on a date with me? Like 1 in 1,000?" And she's like, "More like 1 in 1,000,000." Like, so you're telling me there's a chance? And so, like, even if there's something very, very unlikely, like winning the lottery, there's still a chance, but it's very, very, very unlikely. So 1 in 1,000,000 is a very small number, and it's very, very unlikely to happen, but it's still possible. And given enough times, it will happen a few times. Does that make sense? We okay on that one? All right. So I want you to try this one. So there's a park. It has 538 trees in it. You pick 40 of those trees at random. You look at 40 of these trees, and you figure out what their species is. You find 25 of those 40 that you looked at are maple trees. So we want to find two things. We first want to find what is the experimental probability that if I randomly pick just a tree in this park, it will be a maple tree. And then I want to figure out how many trees in the park should be maple trees based off that probability. So first figure out how many trees are maple trees, and then figure out how many trees should be maple trees in that entire park.
Can you put that on the...
So to find our experimental probability, we're always basing that off of our observations. So what did we observe? So we looked out at 40 different trees, and 25 of them were maple. So 25 out of the 40 trees is our observation. So once again, experimental probability is always based off that observation. It's not necessarily what should, or based off theoretical, but we'll look at those. But it's based off that observation. So if we divide 25 by 40, we should get 0.625. So that's our probability of getting that maple tree. That's the experimental probability. And then if we want to use this, make an inference based off this probability, we can infer about the totals using that probability to figure out, okay, how many in total trees in this entire park? So we'll know, if, well, it's a 6.25 chance of finding a tree out of, or it being maple if I just look at one tree. If I multiply that by 538, the total number of trees I should have should be 336.25 should be maple trees. But then we come back to that thought, okay, can I have 0.25? So I'll round down to 336. The 336 maple trees should be in that park. Once again, this isn't experimental probability, it's a probability. I could have 2 maple trees. Well, I should have at least 25 if we check that. So I should have at least 25 maple trees, but I could have all of them being maple trees. I could only those ones being maple trees. It's a probability. It should occur. That should be the number we should get, but it won't always happen because we don't live in a perfect everything. Make sense? Are we okay with that? So this was experimental probability. Experimental probability, once again, was always based off those observations. Now we're going to talk about theoretical probability. So theoretical probability is based off of what should happen. So based off my knowledge of the events, without performing any observations, without getting out the dice or flipping those coins, without doing any of that, I should be able to think about the outcomes. I should be able to think about what I'm looking for and create that probability. So, for example, if I want to find the probability of getting like a 7, let's do the probability of getting a 3 on a 6-sided dice. I just want to roll a 6-sided dice and I just want to get a 3. Well, I have one desired outcome that's getting a 3. And it's a 6-sided dice, so I have 6 total outcomes. So 1 over 6 would be my probability. What was that? And so 1 over 6, which should be like point something something. Point like 1, 6, 7. Should be like my. So theoretical probability, we didn't do anything. We didn't do any observations. This is just based off our knowledge of what should happen. That's theoretical probability. You won't ever have those observations. No one ever went out and rolled a dice 600 times to see what the odds were. We're just using it based off of our theories. Does that make sense between the difference between the two? And so this one we might have to think a little bit more. So let's say we want to find the probability that when rolling 2 standard dice, so I have 2 6-sided dice, I want to see what happens if I roll them, how many times do I get a 7? What is my total of getting a 7? So we have to think of 2 things. We have to figure out, 1, how many desired outcomes are there? How many desired possibilities will give me a 7? And then how many total possibilities do I have? So what are some possibilities? If I roll 2 dice, what are some things I could get? I could get like a 1 and a 1, which would equal 2. I could get a 1 and a 2, which would equal 3. I can get a 1 and a 3, which would equal 4. I can keep going with that, or I could think I could get a 4 and a 1. I can get a 4 and a 2. I can get a 4 and a 4. There'd be a lot of possibilities, right? So sometimes it might be a little bit easier to create a chart to help us. So I'm going to create a little graph, or a little chart to help us sort of keep track of our data. 1, 2. So we think about these 2 dice. One of my dice, if I roll it, it has 6 possibilities. It could be a 1, it could be a 2, it could be a 3, it could be a 4, it could be 5, it could be a 6. So that's all the possibilities for that one dice. If I roll my other dice, it has the same possibility. It could be a 1, 2, 3, 4, 5, or a 6. So those are all the possibilities for my second dice. If I roll 2 1s, I get a 2. If I roll 2 and a 1, I get a 3. If I roll 1 and a 3, I get a 4, 5, a 6, and 7. Great. Alright, so here's my 7. Well, if you keep going with this, I can think, okay, a 2 and a 1 give me a 3, a 2 and a 2 give me a 4, a 2 and a 3 give me a 5, 6, another 7, and then an 8. What other possibilities will give me 7? 3 and 4 should give me a 7. 4 and 3 should give me a 7. 5 and 2 will give me a 7. 6 and 1 will give me a 7. How many total desired outcomes do I have? 6. I have 6 possibilities of combinations that can give me a 7. So my probability of getting a 7 is 6. How many total possibilities do I have though? 36. I have 36 total different combinations. So 6 over 36 are my odds of rolling a 7 on 2 standard-sized dice. So if you're playing Monopoly, 7 is going to be the most common thing you're going to roll. 1/6 of a chance. 6 out of 3. 0.167. So once again, we didn't roll dice. We didn't take two-sided dice and roll them a bunch of times and see how many 7s we got out of all the times we rolled. We just based it off of our knowledge of what's happening. So that we just use theory for this. What if I want to try to figure out how to get a 9? How many times will I get a 9? Or what is my probability of getting a 9?
Is there any?
Well, let's see.
Wait, actually.
What combinations can I get a 9?
6
6 and 3.
and 3 and 6. 4 and 5 or
5 and 4 is a 9. 4 and 5 is a 9. So for getting a 9, I have 4 over 36 chances, which is 0.11. Are we okay with that one? What about rolling a 13? Possible. The highest number I could possibly get is 12. So the probability of rolling a 13 is going to be 0 out of 36. There's 0 options, 0 desired outcomes out of 36 outcomes, and so 0 minus. We okay with this? So once again, not every time you'll want to create a huge giant chart like this. It just made it easier for us to organize our data and figure out how many total outcomes. Sometimes it's hard to figure out what the number of total outcomes is. Sometimes it's hard to figure out how many desired outcomes we have. We could keep going with that 1 and 1, 1 and 2, 1 and 3, and find all the ones that equal 7. That's one way to work with it, but that's a lot of work to deal with. So we want to try to figure out what is the easiest method of finding out. Typically, the situations won't be too crazy that you won't be able to figure out your number of total outcomes, or too crazy that you won't be able to figure out your number of desired outcomes. So that's typically where the hard parts of probability comes in. When it's hard to figure out what this is, or hard to figure out what that is. Are we okay on this one? Okay. We're going to talk about we're going to talk about one other thing today, and then look at one other problem. That's where we'll cut it for today. So with probability, you have the probability of an event. But whenever you're looking for the probability of an event, we also get the complement. The complement of anything is what is the event, or it's the event in which all of the possible outcomes in which that event does not occur. So if I'm looking for rolling a 6, the complement of rolling a 6 would be rolling a 1, 2, 3, 4, 5. Anything but a 6. So our complement is always the opposite. It's the probability of rolling something that's not that. Or if you think about probability of rolling a 6, the complement is probability of rolling not 6. You can always just put that not in front of it. So if we were thinking, so looking at this, we want to figure out what is the probability of rolling less than a 3 on a standard dice. The probability of getting a number that is less than 3. Well, the only numbers that are less than 3 on a standard dice are 1 and 2. So I have 2 out of 6 chances, which is just a 0.33 probability. Are we okay with that so far? The complement of this event, what's the probability of rolling less than a 3? And whenever we talk about the complement, we always put a big C or a little c at the top to show us the complement. So it's the probability of rolling less than 3, but it's the complement of that. It's not the probability of not rolling less than 3. And so what we do for this is we think, what are the options of not getting less than a 3? What are all the numbers that you could roll that's not less than 3? That's 3 or greater. So I have a 3, a 4, a 5, or 6. So I have 4 out. So 4 out of 6 is my complement, because it's anything that's not this, which is 0.67. Are we okay with that, where I pulled those numbers from? So I was thinking, what are my options, or what are the possible numbers I could roll that are not less than 3? So if I think about the other numbers that are not less than 3, I have 3 is not less than 3. I have 4 is not less than 3, 5 is not less than 3, and 6 is not less than 3. So I have 4 numbers.
So 7, 8, 9, 10.
But this is just a normal 6-sided dice.
Are we talking about dice? Oh, I know we were talking about dice. Never mind.
Standard 6-sided dice. Sorry.
Okay.
What do you notice about the answers to both these problems? Factor, is
The
that what you-
factor or the.
Not quite. They're 33 and 6.7 are close to being double because it's 1/3 and 2/3.
Are we talking about like the fraction?
About the two answers. What do you notice about the two answers together?
They add up to equal 100.
They add up to equal 100. Because if you think the probability of event, and you think of what are all the events that aren't that event, it should be everything else. And so altogether it should be 100. So a probability of something, say event A, probability of some event, plus the probability of that complement of the event should always equal 1, or should always add to equal that 100%. And so we could use this in vice versa. If you're looking for the probability of A and you know the complement, you can just subtract them. Or if you know the probability of the complement and you're looking for A, or sorry, if you're looking for A, or if you're looking for the complement and you know A, you can just subtract the other and solve for it. So sometimes it might be easier to do this rather than thinking of everything that's not what we're looking for. Does that make sense? But always together, they should always add up to equal 1. So if you already have this, and you're looking for the complement, just subtract this from 1, and you already have your answer without having to think through it or do any of that theoretical probability. So we'll look at one final problem, and that's where we'll hold it for today. So there's a jar. It contains 10 red marbles, 8 green marbles, 5 blue marbles, and 6 white marbles. So what is the probability that you randomly reach into that jar and pull out a marble that is not green? So you're looking for a marble that is not green. See if you can figure that out. Once again, there's multiple ways to go about solving this problem. So the way Alex might have done it might be different from the way Gage might have done it. That's okay. Multiple ways to solve it. We're looking for the probability that you randomly reach in and you get a marble that is not green. So, yes, do you have a question? So you're looking for. Okay. So we're looking for a probability of getting a number that is not green. So if we think it's always desired outcomes divided by total outcomes. So how many total marbles do we have?
29.
29. If we add up all of those marbles, we get 29. Now, looking at all those marbles, how many of those marbles weren't green? 21. So you could add up your red, your blue, your white, or you could think, okay, I have 29 total, and 8 of them are green, so I can subtract that to 21. So 21 out of my 29 marbles aren't green. We could then divide that, and that should give us our 0.72, I think. Yes. So 0.72, 0.724, or something like that should be our answer. That's the probability of getting a marble that's not green. So that's one way of doing it. Another way that you could think is, well, probability of not green is the same as the probability of the complement of green. Probability of everything but the green marbles. Which you could think, okay, I know one is all of my marbles. I just need to subtract my 8 out of my 29 marbles, which is my probability of my green marbles, and that will give me my answer. So that might have been another way to solve it, which should still give you the same number. Okay. So it might have been easier to recognize, oh, there's only 8 out of 29 green marbles, rather than having to figure out, okay, how many of them are not green. So some situations it might be easier to do this way. Some situations it might be easier to do this way, but they'll both get you the same answer. They both are the same thing. Just two different ways of working on the same problem. One way it might be easier, one situation where it might be easier to do the complement would be, for example, if you have a large group of things or a large possibility, but you know what the probability of your green is already. If that was given to you, then you can just easily throw that into yourself rather than having to calculate everything else. Are we okay with this? Probability of red, same idea. We just do our 19 over 21 or 1 minus 10 over 21 or 29, I'm sorry. So that's where we'll pull it today. Tomorrow we're going to talk about tables and how can we use tables and frequency tables to talk about probability.